ですね、時間になったかな。これは、どこを見れば視聴者数が見えるのかよくわからない。ですね、いずれにせよ、第4回、サスキンドのクオンタムメカニクスを始めたいと思います。それで、どうすればいいかな。これね、顔は私じゃないんですけど、古賀先生っていうことでやってます。それで、一番わかりやすいのは、ツイッターでハッシュタグサスキンド QM これね、ハッシュタグサスキンド QM で探してもらえれば、こういうふうに、出てきますので、その中で、例えば、コンパスに行きますと、コンパスに情報が載ってます。で、コンパスのこのフィードのとこに質問、コメントを入れていただいても OK です。で、コンパスから、リンクがついてて、ブルーキャットのブログにこういうふうにリンクがついてます。で、ここでもあれですね、下の方に行ってもらって、これコメントを入れていただくことができます。ここでコメントとか質問とか入れていただいて結構です。あとは、こういうふうに言って多分エコーしちゃうと思うけど、YouTube、今やってる配信の YouTube の、ここでもこのチャットに入れられると思いますし、これコメントを入れていただくことができます。配信が終わった後にコメントとか質問とか入れていただいて、配信中はチャット。ちょっと配信中のチャットは読めないかな。今いろいろ画面開けないので読めないです。で、これサスキンド QM のハッシュタグつけたので、それを押してもらえれば、ここに、スケジュール、を、答えられることになってます。それで、実は、3月1日4時からっていうのは、ここハッシュタグがついてないので、そのスレッド表示っていうのスレッドをたどってもらって、上に行くと、明日の朝、午前中は9時、10時、11時、できますので、希望者の方がいれば、ここで、このアンケート機能でクリックしていただくと。ツイッターアカウント持ってない人は、コンパスあるいは、ブルーキャットの、フィードのとこね、に入れてもらうとか、YouTube のチャット欄に入れていただくとか、そういうことで、私にお知らせいただければ、最低1人希望者がいれば、開催します。で、一応今日、14時からの枠が希望者1人いて、で、このままその間の希望者がいないとすれば、次は3月3日の夜9時からっていうことになります。ちょっとこれ、このアンケート機能の期限を間違えちゃって、あと20時間しか答えられないんですけれども、締め切った後はもう一回このアンケートを作り直すので、これで答えてくださいと。そういうことかな。そしたら、続きどうしようかな。ストリームなので追いかけ機能を使えば、最初から1.5 倍速とかで見ていただければ、十分追いついていけると思うので、続きをやりたいと思います。大丈夫だよね。多分大丈夫だと思うんだよ。これで。はい。で、8.4 節。Commutators and Poisson Bracket ということをやります。Earlier in Lecture 4, we formulated two important principles about commutators。これはちょっと飛ばしちゃったところなので、これ改めて説明しないんですけども、コミュテーター、交換子に関して、2つの、いけるか、大事な原理を話したと。The first had to do with the connection between classical mechanics and quantum mechanics。そうね、古典物理では、古典力学ではポワソン括弧っていうのがあって、古典力学でポワソン括弧が使われていたところが、量子力学ではコミュテーターっていう交換子が代わりに使われるよっていうことが最初のこと。Second had to do with uncertainty。2つ目は不確定性について、不確定性っていうのがコミュテーターと関連がある。だから2つの演算子が交換した場合はその両者が同時に確定できると。で、2つの演算子が交換しなかった場合はその2つの演算子が演算子で与えられる物理量に関して不確定性が生じると。そういう意味で2つ目のはコミュテーターとアンサーテンティが関係あったよということをやりました。I now will finish up this very long lecture by showing you what these principles have to do with X and P。このコミュテーターの2つの原理に関して、X と P の2つの演算子が X と P の場合は、どういうことになっているのかということを、示して、この話は、コミュテーターに関する話は終わりにしようと。そういうことですね。We will start with the connection between commutators and classical physics. As you may recall, we found that commutators have a great similarity to Poisson bracket, a relationship we made explicit in equation 4.21. If we plug in the operator symbols L and M that we've been using in this lecture, we get L commutator with M in quantum mechanics is IH bar Poisson bracket LM in classical mechanics. So this is a quantum mech. We use a commutator. Classical mech. We use Poisson bracket. Poisson bracket, I have to explain. This order is difficult. So L, M, Poisson bracket. This is more like LL, del P. Hey, I have to have summation. I, del L, del P, I, del L, del M. Let me see, is this correct? I think so. PQI minus. Is it minus or plus? Minus. Del L, del QI, del M, del PI. This is Poisson bracket. Let me see, let me check. Poisson bracket. See, this is the Poisson bracket. QP, PQ, QP, PQ. Sorry, I'm wrong. This is QP, PQ, QI, PI, PI, QI. This is like LM, 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 LM minus LM, QP, PQ, QP, PQ. That's a Poisson bracket. So we use, instead of Poisson bracket, we use commutator in quantum mechanics. Okay, and we are reminded that the equation for quantum motion strongly resemble their classical equivalents. We are reminded that equation for quantum motion strongly resemble their classical equivalents. This is like a Heisenberg picture. Here, okay. This is like here is Heisenberg picture. If you use Heisenberg picture, equation for quantum motion strongly resemble their classical equivalents. This suggests that we may learn something by computing the commutator of the observables x and p. We may learn something by computing commutator of the observable x and p. Fortunately, this is easy to do. I don't know. We may learn something. What? We may learn something, but what can we learn by computing the commutator of the observable x and p? Fortunately, this is easy to do. So let's just try, then see what we can learn by commutator. That's the idea. First, let's see what the product xp does when it acts as an operator on arbitrary wave function psi x. Okay, so we just let's see what this product does when it acts on arbitrary wave function psi x. Okay, if we act x on psi x, we get this. If we act p on psi x, we get this. Yeah. Let me see. Let me check. If nothing. No. Okay. Together, these equations tell us how the product xp acts on psi x. xp. Now we are here. Now we have product xp act on this. Yeah. But then we can remove this bracket. So we can interpret this to this. We act p on psi, x act on this. Yeah. So this is a psi. this things come from this thing, and this thing come from here. Easy, okay. Then we have x acting on other, x is here. Yeah, now let's try with x and p in the opposite order. Okay, so this is the result. Let's see. This is the result when we acted xp on psi x. This is the result. Now we try acting px, the product px on psi x. That's what we try to do next. We have this px psi x. This is like this. You have this is x psi x. Then we act p on x psi x. So the result is this. To calculate this last expression, we just use the standard rule for differentiating the product x psi x. Using this rule, it's easy to see that. So this thing is like this. This thing is psi x plus x d psi x dx, because dx equal 1. So here 1 is hidden. Yeah, so we just use the standard rule for differentiating product x psi x. Using this rule, it is easy to see that px psi x equal minus ih bar x d psi x dx. This is the second term. This one is this. Then minus ih bar psi x. This is the first term. Now we will subtract equation 828 from equation 827 to show how the commutator acts on the wave function. Yeah, this is a commutator by definition. Commutator xp. This is by definition. xp minus px. So we just see xp minus px acting on psi x. So this means this xp acting on psi x minus px acting on psi x. So then we just calculate. We calculate this one. We calculate this, then we obtain this. In other words, when the commutator xp acts on any wave function psi x, all it does is multiply psi x by the number ih. So we see ih bar and commutator xp, this become equal to each other. We can express this by writing commutator x, p equal IH bar. This in itself is extremely important. これ自体 in itself, this in itself, これ自体 very important, extremely important. The fact that x and p don't commute, so this is commute, xp equals 0, this is commute. This one don't commute. Is the key to understanding why they are not simultaneously measurable. But things get even more interesting when we compare this equation with equivalence. 826, which relates commutator to classical Poisson bracket. Yeah. If we equate, see, this one is classical. So what does this mean? Is this IH bar? Okay. So let me see. Where is my? We can equate xp equal IH bar. Then this part in classical mechanics has to be IH bar x Poisson bracket p equal IH bar. That means x comma p equals 0. No, 0. This is 1. Okay. Interesting when what I did is this one, which relates commutators to classical Poisson bracket. In fact, equation 829 suggests that corresponding classical Poisson bracket is x, p equal 1, which is exactly the classical relation between coordinates and their conjugate momentum. You can just apply a definition. So this, by definition, this is like del x del x dot del p minus del x del p del x. So this is 1. This is 0. This is 1. So 1 minus 0 is 1. So this is the same. Ultimately, it is this connection that explains why the classic quantum concept of momentum is connected. Ultimately, it is this connection that explains why the quantum concept of momentum is connected to the classical concept. I think this is difficult. difficult. So don't worry. I don't think we should worry about it. But this is actually same. See, in classical quantum mechanics, x, p equal IH bar. Yeah? In classical mechanics, Poisson bracket x, p is 1. So in this sense, quantum mechanics and classical mechanics states same thing. Okay, let me say something. I forgot one thing. So we can go to, look at this. We can go to SusskindQM, and then we can go maybe the blue cat. Okay, so then we can see here. You can click this. Then you can download PDF. Okay, so you can download the PDF. Then you can open your textbook by yourself. Okay, so let's see. And another thing I want to check is if there is anybody watching. Seems like there is nobody. Four times watched. 4 times watched. Is this live? I don't know if I'm opening a live. Anyway, is this working? 3時間前. Oh, something is wrong. Okay, this is wrong. 最新. This one, maybe. I don't know if I'm opening. One person is watching. One person has to be me. Anyway, I think I'm working by myself. Anyway, so using the general uncertainty principle from lecture 5, we can now specialize to the case. Using the general uncertainty principle from lecture 5. We can specialize to the case. X, p equal IH bar and del x, del p is larger than 1/2, H bar half. We will do that. Using the general uncertainty principle from lecture 5, we can now specialize to the case. This case. But we will do that in the next section. So let's wait for the next section. Now, let's recall the second principle involving commutators. Second principle. What was the second? Involving this is next section, right? Second principle is uncertainty. Uncertainty. So that means this one? I don't know. He just said we will do it. We will do it next section. But it seems like we are already doing this uncertainty part. In lecture 4, we found that two observables L and M cannot be determined simultaneously unless they commute. If they don't commute, you cannot measure L without interfering with the measurement of M. It is not possible to find simultaneous eigenvectors of two non-commuting observables. Simultaneously eigenvector, this means eigenfunctions. Okay. This led to the general uncertainty principle. So this seems like next paragraph, next section. Next section. So we are in the next section. Section 8.5. The Heisenberg uncertainty principle. And now, ladies and gentlemen, here is what you have all been waiting for. At long last, ついにっていう意味かな。At long last. ついに Heisenberg uncertainty principle. The Heisenberg uncertainty principle is one of the most famous results of quantum mechanics. It not only asserts that the position and momentum of a particle cannot be simultaneously known, but it also provides an exact quantitative limit for their mutual uncertainties. At this point, I suggest that you revisit Lecture 5, where I explained the general uncertainty principle. We did all the work there, and now we get to leap. We get to leap the benefit. Leap. 刈り取る。We get to leap the benefit. As we've seen, the general uncertainty principle puts a quantitative limit on the simultaneous uncertainties of two observable A and B. This idea was captured in inequality. Quantitative limit on simultaneous uncertainties of two observable. So you have this one, A, B, observable A and B, and this uncertainty of A times uncertainty of B has to be larger than or equal to 1/2 of the expectation value of this commutator absolute value. This is the general uncertainty principle. Now, let's apply this principle directly to the position and momentum operators x and p. In this case, the commutator is just a number, and its expectation is that that same number. Okay, replacing a and b with x and p gives this, and replacing x commutator with p with I h bar results in this. But psi equals 1 because this is normalized, and the end result is delta x times delta p is larger than 1/2 h bar. No experiment can ever beat this limitation. No experiment can ever beat. Can ever. なんで ever って。Anyway, you can try your best to determine a particle's momentum and position simultaneously in a reproducible manner, but no matter how careful you are, the uncertainty in the position times the uncertainty in the momentum will never be less than 1/2 h bar. As we saw in section 8.2.1, the wave function of an eigenstate of x is highly concentrated about some point x0. In this eigenstate, the probability is also perfectly localized. On the other hand, probability p of x for a momentum eigenstate momentum eigenstate is uniformly spread over the entire x-axis. わかるかなこれ。Uniformly spread over the entire x-axis. To see that, let's take the wave function in equation 8.17 and multiply it by its complex conjugate. So this is the definition for px. P of x is this. Just wave function absolute value square. You can also write this psi px absolute value square, and you will obtain this 1/2 pi. So this probability density is constant. The result is completely uniform, with no peaks anywhere on the x-axis. Evidently, a state with definite momentum is completely uncertain in its position. Figure 8.2 illustrates the definition of uncertainty for the position variable x. In the top half of the figure, you can see that the uncertainty delta x is a measure of how spread out the function is in relation to its expectation value x. Where is it? This one. Uncertainty basics. So this is the wave function absolute value square, and you see there is average expectation value of x is that's the center of this wave function absolute value square. Then d is defined to be x minus expectation value of x. Then there is a delta x curve to the right of origin. Origin shifted right, So now we set the origin to the center of the wave function. Uncertainty basic stop x expectation value to right of the origin. Deviations d may be positive or negative. Overall uncertainty dx, which is larger than 0, derived from the average value of d square. Bottom, origin shifted right so that x expectation value is 0. Delta x has same value. This is almost the end. So, such figure 8.2 illustrates the definition of uncertainty for the position variable x. In the top half of the figure, you can see that the uncertainty delta x is a measure of how spread out the function is in relation to its expectation value expectation value of x. The label D shows the deviation of 1 point. 1 point in relation to expectation value of x. This may be a positive or negative quantity. The uncertainty delta x is the result of an averaging process over all possible d's and characterize the function as a whole. To prevent the positive d's from cancelling the negative ones, each d value is squared during this averaging process. The bottom half of figure 8.2 shows how the calculation can be simplified by shifting the origin to coincide with the expectation value of x. The numerical value of delta x is unchanged by this shift. Okay, so let me see. Particle dynamics. So we can continue from 273 page next time. Okay, 273 next time. So please request next time. You can click SusskindQM. SusskindQM, then you can just choose. Let me see. So there is also, I have time here, like tomorrow morning and other time. So please choose the time so that I can open the YouTube live next time.